And we're back. So last video we looked at how to find derivatives in polar. Now we're going to look at how to find area in polar, and specifically we're going to look at the area of a petal of that cosine graph we did before back in 10.1. All right, so area is a little different in polar because we're not making rectangles, we're making sectors. So like as we go out and we graph, we go out a certain distance along a certain angle, then we go up a delta theta or a d theta, and then we go back and we make these little sectors. And here's one blown up over here. So the area formula for a sector from geometry is the area is 1/2 theta, the angle inside the sector, times your radius. And we just assume both radiuses are the same when we're approximating, just like we did with rectangles. And we make those sectors really, really small by making theta go to 0, by d thetas or delta thetas. And that ends up getting us an infinite number of tiny little areas to sum up, which turns us into integrals. All right, so if you, just want to think about a circle, theta is 2 pi. So that means the area of a circle would be 1/2 2 pi times the radius squared. The 1/2 cancels out, and we get pi r squared, and there's our circle formula right there. All right, so what we do, again, is we make these little sectors where r is some sort of function of theta, right? R usually is equal to something in terms of theta. All right, so we get 1/2 delta theta times our r function squared. And we just sum up an infinite number of those, so it turns into an integral, which ends up looking something like this guy here. 1/2, there's always that 1/2 out front. Sometimes we use tricks though to get rid of it. We go from an angle alpha to an angle beta. So like angle alpha is here, angle beta is the other end here. And we've got r squared d theta. And usually we plug in whatever r equals in terms of theta, and that will give us the area of this little sector here, right, between angle A and angle B. And whatever our function is, r. All right, so here's an example. Find the area of one petal of the rose given by r equals 3 cosine of 3 theta. All right, so I think we looked at this one before. Actually, we used 2 before, but it's not going to change much. We're still going to have, when we plug in 0, we're still out there at 3. And then by the time we get to, let's see, what was it? Pi over 3, was it? Yes, cosine starts high, goes down. This is ordinarily 2 pi, so this is ordinarily pi. This is ordinarily pi over 2. But now we're dividing everybody by 3. So this would be pi over 6, this would be pi over 3, and this would be 2 pi over 3. So by the time we get to pi over 6, looks like we're back to 0. All right, and if we want to go the other direction, we could just go to negative pi over 6 and it'd be to there. So this is pi over 6, and this is negative pi over 6. So one rose, which again, we can use any one of these petals we want to, would be, the area of it would be the integral, or 1/2, remember 1/2 r squared d theta from alpha to beta, angle A to angle B. So it'd be 1/2 the integral from negative pi over 3 to pi over 3, not 3, 6. I was looking at the 3 here. I was getting ahead of myself. And then we've got r, which is this guy. So 3 cosine of 3 theta squared d theta. All right, so we can try and integrate that. We're going to end up getting cosine squared. It's not the easiest thing to integrate, right? We'd have 1/2 the integral from negative pi over 6 to pi over 6 of 9 cosine squared 3 theta d theta. All right, not exactly something easy to integrate. We'd have to use some trig identities to integrate that, or the calculator. All right, now there's a trick here. This rose, this petal is symmetric, right? The top half matches the bottom half. So one thing we could do is say, okay, well, let's go from angle 0 to pi over 6 and then just double it, because that would be this area. Just doubled would be the whole thing. So we could also say that this is 1/2 times 2 times the integral from 0 to pi over 6 of 9 cosine squared of 3 theta d theta. And now this 2 and the 1/2 cancel. All right, so we often will do that sort of thing. We'll say, okay, what's half of what we need? And then just double it, and we'll get rid of that 1/2 out front. It's a sneaky little trick. All right, now this 9 can move out, and we can just take the integral here. It's probably easiest if we just throw this in our calculator and see what happens. All right, so you actually don't even have to be in the polar mode in your calculator. It will still integrate perfectly fine. if it'll turn on, but I am still in polar. So math 9 for my integral. I'm going from 0 to pi over 6. All right, I've got the function 9 times cosine of 3 theta. All right, and it does type theta because I'm in polar, but if you typed it with x, it works fine. Squared. All right, so I didn't square the 9, I squared the cosine just to make sure. Yep. And again, the variable I used was theta. You could do this with x and it would work just fine if you're not in the polar mode. And there's our answer, 2.356. All right, so that's the area of one petal. If we wanted the area of all 3 petals, we would just do that times 3. All right, so that's one of the tricks we use often when we're doing areas of petals or shapes or things like that, is we find one of them, and then we could double it, or we find half of them, and we double it to find the whole thing, or we find one of them, and then we could triple it to find all 3. So we could find the area enclosed by all 3 petals. So this is the area of one petal. If we wanted the area of all 3 petals, or the area enclosed by the curve, we would say it's just 3 times that. We might want to keep more decimal places if you're doing times 3 and that sort of stuff, but that's again, that's all we're doing. All right. So that is how we do area of a section in polar. The next one we'll do the area between 2 sections. So again, we'll do some more, so don't worry, there's more coming.